So we will have introduction of computational material science in this in today's lecture. So here is the outline of lecture today. So firstly, we will make a short, brief introduction of computational materials, and then we will show why, how, and what to do about computational material science. And I will show you a brief example about the workflow of typical computational material science work. So for the state-of-the-art material science, we typically classify the materials science by the materials type. For example, we have polymer, we have metal, ceramics, or electronic materials. For the polymer, this kind of material is treated as a soft material, which is widely used as a part of the composite material or some of functional polymers like conducting polymers or other kinds of polymer that used in optoelectronic device or biomedical polymers. So for metal, we may have topics that about functional alloy or aerospace materials, metallic glasses, or a very new topic, high entropy alloy. For ceramics, we may use it as a piezoelectric device, and it is known as a piezoelectric ceramic. And it can be treated as a part of composite materials, or we use it as high K materials in the semiconductor device. And also, in some cases, we will treat it as biomedical material, such as artificial bones in our body. As for electronic material, it is typically known as semiconducting materials. So we typically use these kinds of electronic materials in photovoltaic device, such as a solar cell or photodetector or any other kinds of transistor or your IC chip in electronic device. Or we may use some of low-dimensional materials, such as graphene or MOS2, such kinds of low-dimensional materials in some very fancy usage. And for the most important one, we use these kinds of electronic materials in many kinds of commercial electronic devices, such as your mobile phone and a notebook, your iPhone, your MacBook, and any kinds of electronic device in our life. So what is material science in our imaging? So we know that, so far, the material science is treated as experimental science, which means we have to make it by our hand. We have to do many kinds of experiments. We have to we have to do some measurement. We have to synthesize materials we want. And for the research method, such kinds of experimental science, we typically search for the cause and effect relationship by the observing and measuring. So for any kinds of observable or measurable value, it is typical macroscopic value, or we just view it from a macroscopic viewpoint. And the research method are strongly related to the type of materials. For example, the research method for ceramics or the research method for metal, one of the well-known research methods is electron microscope. However, we cannot apply the analysis by the electron microscope on the polymer because the polymer would be breakdown in microscope, and the microscope would be also broken. So, if we want to make a very detailed research of any kinds of material type in our research, we have to learn a lot of different analysis methods, and we have to make sure this method is good for our targeted material, and it won't break our device. Indeed. So we still have other issue that's about the effect of experimental science in material science. However, as for experimental science, we will meet many kinds of critical issues. For example, previously we have mentioned that we are trying to observe, we are trying to measure something about our targeting material. So these kinds of target, we can only use measurable value as our target if we deal the problem as experimental viewpoint. And typically, the research of experimental science is typically follows trial and error methodology, and the detail of the reaction is unclear because we can only get the result after all experiments was finished. For this reason, it is hard to construct a convincing mechanism because we didn't know any detail about the reaction. So once if we have made some mistake in experiment, unfortunately, we can only observe the poor result in the final stage, and then we have to redo a new one, and then we have to spend a lot of time, money, human resource, apparatus, and we have to buy the materials again, and still, it is quite hard to find the actual reason that caused the mistake. So, in this case, if we have made some mistake, and then we just redo one, and we still have a chance that we have made exactly the same mistake, and we still have to redo a new one. So if we examine the material science from the experimental viewpoints only, we have to meet this kinds of dilemma, and we have to find some method to solve it. So if we change our viewpoint, we just apply the computer in helping us to understand the detail of the material science. So this kinds of research method is called computational material science. And in the computational material science, we treat a computer as a tool in solving various materials problems. So the advantage of these kinds of research is because the computer is a tool, we can apply this tool in dealing with any kinds of material system. In comparing to a real experiment, the computational material science is typically less consuming in time and the resource. And it is quite easy to check the latest state by viewing the log file during the work of computational material science. But the disadvantage of computational material science, it's just like what we made in the computer science. We have to make sure our input data is good enough. If our input data is poor, which means we just put some garbage in the computer, the computer will still give you a solution, but it should be a garbage. So we typically call it a garbage in, garbage out. And if your input data is not that good, it may give you a partly correct and partly wrong result, which means you have to distinguish which one is good and which one is a fake result. So below is a computer, a schematic plot of a computer that used in computational material science. We call it a cluster, which means this kind of cluster is a bunch of computer that consists of many CPU and a lot of RAM and just parallelly connected one another. And then if we import data through our desktop computer, the cluster, computer in the cluster can do our request calculation, and then you will get calculation result when the job is finished. So what we want is your input data is good, and your research method is good enough, which means you have a good physical model, and then you will get a good result. However, in real life, we typically face either your model is not that good, or your input data is poor, or both your data and your model is poor. So if so, you will get a poor result. So as for the computational material, the research in the computational material science, what we want is just make sure your data is good enough and your model is good enough and your result is good enough. So once if you meet a poor model or poor data, please try to correct it, or please try to make sure it is, we have to fix it during the calculation. Previously, we have mentioned that typically we use cluster computer in doing computational material science. And another kinds of, or another name of a cluster is, which is known as a supercomputer. And below is Taiwan NEA 2, which is one of the most powerful cluster, or most powerful supercomputer in Taiwan. If you have an interest, you may just search it in the Google, and you will get a full introduction about this powerful computer used in computational material science. So, why we have to do a simulation? Why we have to use a computer in helping us to do material science research? So here is an example. So in this research, the scientists have tried to synthesize a bunch of perovskite materials used as used in the solar cell device as absorption materials. And you will see once if we put more and more components in perovskite's substrate, we will get higher efficiency. So in this research, they just use the MA, FA, PB BR&I perovskite, which contains a lot of 5 components and a lot of different elements. And they just pick 7 different composition for Ma and Fa and for Br and I individually. And they just synthesize 49 different composition of perovskite, and they just measure the morphology, measure the color, and all of related parameters of solar cell device. That includes short circuit current, power conversion efficiency, field factor, and open circuit voltage. So they can get the below chart in showing a relationship between these parameters and the composition. So as for any material scientist, all of us want to know the actual relationship among the structure, which contains the idea of morphology, defect, and packing ratio, density, diffraction pattern, any kinds of issue that related to the electronic structure of your materials, and the processing parameter that includes the type of element and the composition and the temperature, the pressure used in the synthesize your material, and the method of synthesis, and any kinds of processing parameter. And finally, the materials property, for example, the electronic property, optical property, mechanical property, and any other kinds of property. So for a scientist, we all want to know, we are trying to get the actual relationship among all factors in the structure, process, property relationship. So in the previous paper, they have shown the relationship between the process and the structure. They have shown that the different composition of a perovskite material would give you a different morphology of under the electron microscope in the lab part. And they have already shown the process property relationship. They show that what kinds of composition would give you a good power conversion efficiency, would give you a higher short circuit current, would give you a good field factor. So although they have shown the relationship from the measuring result, they didn't provide any reason. So this conclusion is just come from the experimental observation. So they have result-to-result relationship, but no direction, no direct evidence has been provided in this paper. And the most critical issue is that in their paper, they didn't provide any structural property relationship. It is simply because this kinds of structural property relationship is not available from any kinds of research, from only experimental observation. So if we want to construct the mechanism, we want to know the detail of material system by using experimental result only, we will miss a lot of issue because this kinds of research is lack of direct evidence and lack of the microscopic viewpoint. We only have value comes from a macroscopic viewpoint, comes from a measurement, but we didn't have a microscopic viewpoint. We didn't have any information come from atoms. And the most critical things, we don't have structural property correlation. So this is why we want to do a computational simulation, computer simulation. Because in a computer simulation, we can actually do these kinds of research from an atomic viewpoint. And we may have provide the atomic viewpoint, atomic evidence in showing what experimental they observed in our measurement